first learn about trig ratios, we're usually talking about the ratios of sides in right-angled triangles like this one. So if I was to talk about the trig ratios for the angle pi on 4, sine of pi on 4 would be the opposite side divided by the hypotenuse, 1 on root 2, which turns into root 2 on 2 when you rationalise. Cosine of pi on 4 would be, again, 1 on root 2, the adjacent, divided by the hypotenuse. And tan would be opposite over adjacent, which is just 1. But what we want to do is build up a new definition that lets us have trig values for angles that aren't just restricted to angles inside right-angled triangles. So you can imagine inside a right-angled triangle, the angles have to be adding up to 180 in total. 90 degrees is already taken up by the right angle. So you've only ever got angles between 0 and 90 degrees that you can find sine, cos, and tan of. But it turns out they're really useful when you've got sine, cos, and tan of angles bigger than and smaller than that. So we have to build up a new definition. So this demo is about that. And the idea is that we're going to start with a new definition, but which is completely consistent with what we know from the ratio of right-angled triangles. So the way it's going to work is I'm going to start off with just refreshing some ideas on angles in radian measure. So you can see down the bottom here is a little converter which tells you how many radians you got and how many degrees that is. The angle that we're going to form is using this ray here, a radius, and another one which will go from the origin to the outside of the circle and gradually gets moved around the circle and sweeping out a bigger angle. So for example, there's one there, pi on 6 or 30 degrees. You can see is the angle formed by these two lines. That perpendicular pair of lines, we'll see that comes into play a little bit later on. So pi on 6, pi on 4 or 45 degrees, pi on 3 is 60 degrees, pi on 2 is 90 degrees, and so on around the circle. Okay, so I'm using basically multiples of pi on 3, pi on 6, and pi on 4, and that's because I'm going to work with using those standard triangles that we're familiar with that we use for exact values of trigonometric functions. Okay, so that's the angles. Now, the idea is we're going to bring in some standard triangles and look at some of the other angles that we've got. So this angle, this triangle here, I'm going to call my reference triangle. And you'll notice that no matter what the angle is, it's always going to be a triangle formed with the horizontal axis and a perpendicular line up to the coordinate, which is the end of the radius. Okay, so I'll just show you a few of those. Okay, going around, it's always with the axis, the horizontal axis, sorry, and always a perpendicular from the horizontal axis out to the point that the radius touches on the circle, the unit circle. Okay, so each of these, because it's a unit circle, that means the radius is 1. So that length there of the hypotenuse of that reference triangle is always 1. What you'll see up the top here is a standard triangle, or special triangle, sometimes people call them, 45-degree triangles and the 60-30s, or pi on 4 and the pi on 3, pi on 6. And it's going to be the one that corresponds with our reference triangle down in the unit circle. Now, they're not exactly the same triangle. They're just similar. They're similar because the angles of the triangle will be the same. They're both right-angled triangles, and they're both going to have the same angle that I'm interested in finding the trig values for. And because the angles of a triangle add up to 180, the other one must be the same as well. So they're similar triangles. They're different because they have different lengths on their sides. Up here we've got root 2. Down here we've got 1 because it's the radius of a unit circle. Okay, so we can see if we go up to pi on 3, again, we've got a similar triangle here, hypotenuse 1. Up here, our special or standard triangle has a hypotenuse of 2. So all the sides will be in a ratio of 1/2 with each other. Okay, so that's our standard triangles. You can see them popping around there. Okay, and everywhere we are, we're going to be able to use the reference triangles and the standard triangles to figure out the side lengths. We already know this one's 1, but we're going to be able to figure out what these ones are as well, because all the sides must be in proportion with each other. All right, So let's take a look at, let's have a look at pi on 6 first of all. So remember, the two triangles are similar. Hypotenuse here is 1. Hypotenuse up here is 2. So the side here, okay, will be proportional to this one, and it's proportional. Proportionality constant is going to be a half. You can actually just read that one straight off the graph here. We can see that that's at 0.5 or a half. And down the bottom here, we've got it in a decimal there. I don't like that. We can do it exactly. It's going to be root 3 divided by 2 because it's only a half of our special triangle up the top there. Okay, so we've got 1/2 and root 3 on 2. But remembering our trig ratio definitions, okay, the sine of this angle is the opposite side, 1/2, divided by the hypotenuse of 1, just a half. Similarly, cosine of pi on 6 is going to be the adjacent side, which we just said was root 3 on 2. Again, divided by 1, so just root 3 on 2.
Good.
So we can pop those labels in there. Sine of pi on 6 is a half, cos of pi on 6 is root 3 on 2. Using that standard triangle and our reference triangle and the proportionality between them because they're similar triangles. So in other words, we're able to get all the same results back as what we're used to getting from our trig ratio definitions, but we're going to use that as the basis for our trig function definitions. Everything's fine and the same as always in that first quadrant, the 0 to 90 degree angles. Okay, so you'll see if I bump it up to 45 degrees or pi on 4, there's our special triangle, our standard triangle. It would tell me that the cosine, for example, of pi on 4 is 1 on root 2, which rationalizes to root 2 on 2. Again, down here, if I have a look at my new definition says that the cosine of that angle is going to be the x-coordinate of this point on the unit circle. Okay, the x-coordinate's down here, and because these two triangles are similar, but in proportionality, with a proportionality constant of 1 on root 2, my x-coordinate here is going to be root 2 on 2. Okay, so same thing. Moving up to pi on 3, we can do the same results there. Where it gets interesting is when we go around to the other quadrants. Okay, so now you can probably see this triangle similar to this one, but the proportionality constant is going to be a half, again, because we've got a hypotenuse of 2, hypotenuse of 1. So this side over here must be root 3 on 2, and this side down here is going to be 1 on 2, but notice in terms of our coordinates, it's negative 1 on 2. So that's telling me that the cosine of this angle here, which is clearly not part of a right angle triangle, it's outside of a right angle triangle, cosine of that is going to be minus 1 on 2, something we're not used to seeing because cosine used to be a ratio of lengths, which were always positive. Again, the y-coordinate or the y length of that line there is going to be root 3 on 2, which is the sine, now, according to our new definition, of 2 pi on 3. Okay, let's try another one. Here we've got 3 pi on 4 is our angle of interest. Okay, you can see our two similar triangles. Root 2 divided by 1, or 1 divided by root 2 for our proportionality constant is going to give us the lengths of the perpendicular sides, and therefore, according to our new definition, sine is the y-coordinate, cosine is the x-coordinate, sine of 3 pi on 4 is root 2 on 2, and cosine of 3 pi on 4 is minus root 2 on 2. Okay, so same sort of thing happens around the circle. Notice that we've always got that reference triangle moving from the ray, or the radius if you like, that forms the angle, 5 pi on 4 in this case, back up to, or back down to, depending on where you are, the horizontal axis. It's going to be similar to one of our standard or special triangles, and that's going to help you figure out the length of those sides. Okay, which gives you the cosine, by definition, is the x-coordinate, and the sine, which is the y-coordinate. Again, moving on around the circle, we see the same thing happen. Okay, the only thing that doesn't kind of tell us is what to do on the axes themselves. So when we have an angle like 3 pi on 2 all the way around here to the negative vertical axis. Okay, that's okay. We don't need any of those reference or special triangles because here I know exactly what that coordinate is. The coordinate of that point that the radius goes down to is exactly x equals 0, y equals -1. So the sine of 3 pi on 2 is -1, and the cosine of 3 pi on 2 is the x coordinate, or 0. Okay, so same sort of thing back on the horizontal axis. I know what the coordinate is. I don't need any triangles to tell me that. So the sine is going to be the y coordinate. Here we're at y equals 0. And the cosine of pi, okay, that's our angle there, pi, is going to be the x coordinate, which is -1. Back on up to pi on 2, sine is 1 and cosine is 0, and so on. Okay, so there we go. That's just a bit of a demo of how those values come about for sine and cosine outside of the first quadrant using our special or standard triangles that we use for trigonometric ratios.